You write a quick note for Bridget. 7.3b wasn't supposed to be super long, but it did have some application problems. So even though the problems, there weren't very many of them, it might have taken you a little bit of time and stretched you a bit. Today is the 17th, and right now is 9:02. I'll be 9:00. I have enough for you already. Number 30, you can already be check-in. Oh my goodness, we got a false statement. What does that mean?
You wasted so much time.
No, you did not waste so much time. You just found the solution. You found that it is not a possible problem. There is no possible solution. In science, if you are doing research, it is a good thing if you figure out something is impossible. In math, similar deal. It's a good thing if you figure out something is impossible. All you have to find is one counterexample to negate an entire statement. Anyway, so you just proved that it was impossible. Good job. Number 15. Check out your equations, because before you could ever get to the final solution, you had to get the correct equations. You get the correct equations by plugging in x, plugging in y, and simplifying. There's one equation. Plugging in x, plugging in y, simplifying. There's another equation. Oh, they plugged in C2. There's your second equation. Plugging in x, plugging in y, getting a third equation. Now you've got a system. You could have written it in our stair step. You could have said, like, hey, I know C, yay, plug him in, and then solve the smaller system. Either way, at the end of the day, you end up with negative x squared plus 2x plus 3. They wanted you guys to graph the equation and make sure that the original points are on there by using, like, a second trace or something. With those different xi's, you could have plugged in 0, should have gotten 3, plugged in 1, gotten 4, plugged in 3, gotten 4. Just to check.
I think it's C. Because they said C is equal to 3.
Oh, because if you plug in 0, remember these are points, x's, y's, so 0 would make that 0, 0 would make that 0. C is equal to the y, which is 3. Does that make sense?
Yeah.
Yeah, so for each of these points, you're plugging in to x and to y, and you're seeing what's left, and that made your little baby system. Although he wasn't that small. Number 64, one more time, because a few of you guys seem to be following along. There's the final answer, negative x squared plus 2x plus 3. A is negative 1, B is 2, C is 3. 64. Did you guys have to find this system, or was it given to you? Oh, this was 180s. Hey, that was your geometry one, right? Like yesterday? Where did those equations come from? Something like this. Equals 180, equals 180, equals 180, right? It came from something like this. You were supposed to set up 3 equations, and once you had 3 equations, I yesterday showed that you could move maybe the constants to one side, organize everything to be all nice and pretty. Maybe organize everything to be all nice and pretty. But once you plug and chug, you end up with final answers of z equals 94, x equals 36, and y equals 50. Z equals 94, x equals 36, y equals 50. Remember, if you don't have the right answer, get the answer done. And if there's time, you can check the work and see where you messed up. I guess you could have written that in order, 36, 50, and 94, but it doesn't really matter. You're just solving for 3 different things. And once again, your original system comes from adding 3 angles to 180, adding the 2 angles, I think, to 180, and then adding the other 2 angles to 180. And then, ooh, hey, that's the homework that we're not quite there ready for. Okay, cool, kids. That should have been plenty of time to go ahead and see the answers that you need. Were there any odds? Were there any odds? Because the evens, if you get something wrong, I usually try to explain where the stuff came from. But the odds, like, I already got to check and I knew I got it wrong. What happened? Anything that we got stuck on? Yeah, absolutely. 39 and 47? Okay. Any other ones besides 39 and 47? No? All right. 37 and there's their backwards.
37, 47,
yeah, I think so. Oh, 39 and 47. think 37 might have been the other one.
Yeah, 37 was there.
39 and 47. So, he's taking forever. So while we're waiting for him to come up, let me go ahead and let you guys start taking 7-4 notes because there's some writing to start us off. This might seem a little random, but it's not. Because you're going to need systems to do all, well, not all, but most of 7-4. You're going to need systems, and they're not going to be hopefully really hard systems. The systems hopefully will be easier, but you still need to use those system skills you've been developing in order to solve. Give me one moment just to get to your correct section. I'll be right back to notes. He's not happy. He's loading. He's frozen. Alright, well, let's let you guys keep on taking notes. Hopefully he'll unfreeze one of these days. Partial fractions. In partial, you see parts, right? Parts that go together to make a whole?
Probably.
Sounds logical, right? Or at least somewhat logical if we got to this point. Go back and try one more time. Oh, now it's 7. And it was 39 and 47. Never mind, keep taking notes. E for effort, F in success. Yes, happy Friday. Have I said that yet? Happy Friday before a 3-day weekend. What? Praise. Happy last day of your grading period.
It's fine. Spanish.
Is today a rough day? Did everybody pile stuff on? Not too bad? Any class or quizzes or in-class essays today?
Monday, yeah.
That's what I know of.
Monday, okay. Yeah.
Monday, the stay-at-home day.
Online.
That sounds fun. Working there? Ah, alright, I'll let you guys finish notes for a couple more minutes. I'm all set up, ready to go for us to look at our other questions. Oh, sorry, I meant to hit that one. Wrong one. You guys probably get seasick from all of my changing pages. A little bit. Hopefully we'll find right before it. Question, how can you guys check the example that you see? How can you check to make sure that the two sides actually are equal? What did you do? But you can't add yet, right? Common denominator. Take a second. I want you guys to see if they actually are equal. I'm going to do it, but I'm going to do it quickly. How do you know that the right side actually equals the left side? You need a common denominator, right? Some of you are mental mapping it. That's a bit of a stretch for others. How would you find a common denominator? I want you guys to ponder that question. How would you find a common denominator?
Multiply them by denominator and the other.
Multiply each by the other's denominator, top and bottom. Take a second. Think of it kind of like a T-proof. We're going to make the right side match the left side. We're going to show that it's true and not just take it as fact. How would you get a common denominator? You guys know this. Alright, while you guys are pondering that, we'll come back to that in just one moment. Let's go ahead and peek at 39 and 47. There we go. I might not get all the way through, but we'll at least peek at them real quickly. What's 47? Where is he? Oh, is that the number? Okay, 47 was a lot like the number 48 that we set up yesterday in our notes, so I won't take tons of time on him, but I will show you where to go in order to think about him. And then number 39, ooh, he's also like an example in our notes. So let's go ahead and, number 39, what was weird? Can you guys see it in here? Put the hand by him. Come on, Mr. Hand. Okay. Number 39, what's weird about him? How many variables does he have? He has 3 variables, but how many equations does he have? 2. In our notes, what did we call any equation that has a different number of equations than variables? Non-square. How did we solve said non-square problem? We added in z equals a. We added in z equals a. So my advice would be for number 39 to go ahead and link these two like we would normally do. We normally take the first 2 equations, take it off to the side, cancel out the x terms. Link these 2, take it off to the side, cancel out the x terms. And then, to be honest, if you look at the example from our notes, after you link these 2, take them off to the side, cancel out the x terms, you have an equation with x, y, z. You have an equation after that first link with y and z. And what are we going to set as our third equation without any more work? Z equals a. Then we can go ahead and say, booyah, it's time to go. It's time to solve. So the big step on this one, let z equal a. Start your system, but you don't have to go as far as you're used to going because now you're ready to go ahead and plug and chug. Now guys, why did I do the 1/2 and 1/4 again?
To get the leading coefficient to be
Yeah, to get the leading coefficient to be a 1, so I distributed to everybody. I was just being proper, putting it in the proper form, but could you have just plugged in a and solved for y? Yeah, could you have plugged in z and then whatever you find for y and plug in? Yeah. But when you get the leading coefficient of 1, it kind of makes the math a little bit later easier. Ashley, is that enough to get you started, kid?
Yeah.
Okay. Ricky.
On the test, do we have to make the leading coefficient 1, or can we, if we have a problem like that, where we can find them right away?
The only reason you would need to make the leading coefficient 1 is, first of all, if you try both ways and you like it better, then you should. Or if I ask something about put it in row echelon form, or which of the following are in row echelon form, make sure you get the leading coefficient 1. Does that make sense?
Yeah.
But otherwise, if I just say solve, you can just plug in A's or plug in the number at any point once you have your stair step. Does that make sense? Okay. And then for number 47, he was the weird position-y one, physics-y one, that we didn't really talk about the physics a lot. We just said like, hey, these are like x's and y's, and so we plug in the x's, we plug in the y, and we simplify. I tried to kind of get you guys going on that one, the idea. Here it is. On number 48 in our notes. Where did, because I have these points, which technically, look at number 48, looked just like number 47. It was written differently, but I treated the t's as x's, the s's as y's. What did I do with each of my points? Plug them in. So I had t as my initial value, or as my first value. Each of these points follow the pattern of there's t. Well, hold on, I did something weird because it's like making everything. Huh. What did I hit? Oh, the shapey thing. There's the shapey thing. Okay, all better. Each of these points follow the pattern of t followed by s, which is like your x followed by y. So we plugged in the y values, like 132, plugged that into the y spot, that's why he's over here. Plugged in the t value into the t spots and simplified, and that's how we got this. So just like that other example that we looked at, where you plug in the x's and y's and simplify. For number 47, 48, I should say, and similarly 47, take each of those clues as points, plug and chug them in, you'll get your system of equations, then you solve like you would have any other problem, any other 3 equation system. Because we have 3 clues and 3 unknowns. But if you don't like the b sub 0, s sub 0, the one hint I gave you was you can just make it a and b and s. I won't get super particular about how you name them. You can just name them a and b and s. And those are the guys we're solving for. Does that get you started okay on that one too?
Yeah.
Cool. All right, let's go ahead and get out of this guy and go to section 7.4. If you guys notice, even though trig is gone, the math isn't super easy. But it is much more algebraic than you guys have been used to this year so far. We didn't need this page, I didn't end up using it. Okay. Section 7.4 is no exception. In the sense of, in chapter 7, we're doing a lot of algebraic stuff, and we're going to do that in 7.4 also. Algebraically, in order to add fractions, well, hold on, we got to get common denominators, and that's what you guys were hopefully thinking about. So common denominators, what did you multiply first of all? What did you multiply the 2 over x minus 3 by? X plus 2 over x plus 2, because once again, remember I was having you guys ponder, how do we put these two together? How do we see what they are combined? Because right now they are separate, right? How do we get them combined? We have a big old plus in between. We have our negative 1 over x plus 2. What would we multiply this guy by? We multiply negative 1 over x plus 2 by? By the other denominator, top and bottom, multiplying by 1 creatively. Totally legal. Now, we have to be really careful not to kill any seals. He's our distribution error one. How do I make sure not to make any distribution errors?
Parentheses.
Yeah, we need parentheses like all over, right? All over, all over, all over, all over, all over. To make sure we're doing everything legally. On top, this one, don't we get 2x plus 4? Plus, this one we have negative x plus 3. Doing all right? Why haven't I written any denominators yet? What happens when I did this? Not cancel out, they became
Same.
common, right? And so when you guys did the same, I like that. They became common, so we're going to go ahead and say, sweet, we can put them together. Remember, 1/3 plus 1/3 is 2/3, right? 1/3 plus 1/3 is 2/3. Same thing here. If I have over x plus 2 over times x minus 3 plus over x plus 2 times x minus 3, they combine and stay the same. I have some simplifying though, right guys? Yeah, 2x minus x is just 1x, right? 4 and 3 make 7. And my question is, does the right equal the left? How come? The last thing we would do is just multiply that denominator by FOILing probably. Oops, parentheses. Minus x plus, nope, minus 6. A little bit roundabout, but check, we got it done. Have you ever, in your mathematical career, had to take something like this and get it to look like this? Yeah, probably, you know, here and there. Directions might have been simplify, maybe solve the equation, and we had this original thingy where we're like, ew, gross, the x's are everywhere, we gotta get them kind of all together. You have done that, but have you ever gone backwards? Ooh. Backwards. Huh. Hey, question, is there something else this year that we did backwards? We were used to going forwards and then we went backwards and... I mean, yeah, we did with inverse trig, right? We went backwards because we had to go backwards from the ratio to the angle. Good. Inverse trig, I heard someone say with our trig. Anybody else remember something that we did backwards? Back substitute, that's kind of going backwards.
Also, no, she's looking at
Yeah, not quite what I'm looking for.
Chapter.
Yeah, You guys ready? You don't have to write this down. Let's see if this rings any bells. And then we'll see why on earth I'm bringing it up.
Algorithms. Also not.
What am I asking for?
What is it called? I don't know what it's called.
Whoa! I just went a little crazy. Okay, I had a little too much fun. However, remember what we did with this guy?
What is it called?
We took a composition of functions and we broke them down and said who were the pieces in the composition. Can anybody tell me the innermost?
2xe.
Ooh. Nicely done. 2x is the innermost, so who does he go with?
Okay.
Do you guys see how he's like inside the cosine, inside the squared, under the square root, and inside the e? Poor little 2x, he's like totally stuck. There's no getting out for him. 2x. Who's the next guy? Because remember, he gets plugged into him, right? Who's the next guy? Might be a little hard to see him the way he is. He'd actually be rewritten, don't get tricked by the trig notation. Cosine squared is really cosine squared. So we've done the 2x, we've done the e to the, who's the next guy? The cosine. Who's the next guy?
Square.
The squared. Woo! Who's the next guy?
Square root.
Why'd you write that? It just came from that. Yeah. We cancel out after you and square after that.
But did you know that by the way? Party poopers. Alright, anyway. I was trying to make it complicated, and I did. What was this called? Did anybody figure it out?
Composition.
Composition is where we're putting it all in. You're composing something. You're putting it together. What is it called? Decomposition. You're breaking it apart. You're figuring out its individual pieces. This is actually a huge intro. Now, this is a really hard example. Like even calculus kids who get super freaked out by this. But this is a huge intro to something in calculus called the chain rule. The chain rule has to do with how bunnies can die in my classroom. So sad. Anyway, but coming on back. Why am I talking about decomposition?
Because you just said it was important in calculus.
True, but also, what's this thing called when we take a huge put-together fraction and try to figure out its individual pieces?
Partial fraction.
Hey! No way. We're breaking it apart into its pieces. Now, it's like the composition idea, except it's a little bit harder. For composition, we look at it and say, who's the innermost? Who's the one outside of that, outside of that, outside of that? We're peeling off the layers, like peeling off the Matryoshka dolls. What? The nesting dolls? Anyway. That was a different day, a different topic. This time, we are breaking apart put together fraction into its parts, into its partials is the snazzy term for it. Now, how do we do that? Well, we got some stuff to learn. You ready?
Sure.
Hopefully, at least, though, we can kind of remember the word or the term decomposition for the process that we're going to learn. Let's go ahead and put like a quick little X in case someone's absent to know that that's not the point of today's lesson. And, oh my goodness, life just got scary. Don't worry. Haven't we seen some yucky tables in chapter 7, and don't I usually highlight the important stuff?
Yeah.
So let's do that. Let's start with number 1. The important stuff. Divide when improper. 2, decompose some sort of rational function into its partial fractions. First of all, we have to look at it and say, are you improper? And what does it mean for a fraction or a rational function, which is a fraction of functions, to be improper? 3 at the top is greater than or equal to degree of the bottom. Divide when improper. Degree of the top is greater than or equal to degree of the bottom. Whenever we have an improper function, degree of the top is greater than or equal to degree of the bottom, we have to divide. And how do we divide? We get this from this. Long division. We get what we want from long division. So, whenever we have an improper function, we divide. What kind of division? Long division. Now the nice thing is, very few problems actually need this. We just always have to check for this first. We always have to check and make sure whatever we're given doesn't need long division. If we have to do long division, then we have just broken down our original function into pieces. However, we're going to have to look at the remainder and make sure it can't be broken down any further. So then we take the remainder and then we go to step 2. The non-highlighted, non-written, and red stuff, you can write down if you want, but you don't actually have to. If you're given an improper function, the very first thing is long division. Long division is going to, let me go ahead and show it here. If you have an improper function, the very first step is long division. From the long division, you're able to get the solution. So you've broken it down partially just from long division. But then you have this remainder piece over here. And this remainder piece might need to be broken down as well. So then we go to step 2 with the remainder piece. Now, if number 1 isn't necessary, sweet. We say, is it improper? No. Okay, step 2. So no matter what, we're eventually getting to step 2. Sometimes we go there pretty much right away. Sometimes we have to go there after long division. Step 2 says, factor the denominator. That's it. Step 2, factor the denominator as much as possible. Don't go to imaginary numbers. Not that much. Factor as much as you can while staying with real, rational numbers. So factor as much as is reasonable. So I'll go ahead and highlight completely. Completely means don't go to imaginary. Just go as far as you can while still keeping the numbers nice. Completely factor the denominator. When you completely factor, you might get 2 different types of factors. Depending on the problem, you might get linear factors, which are the ones of the form mx plus b, maybe raised to a power, maybe not. And you might get quadratic factors. Now some of you are like, well that's silly, if they're quadratics, wouldn't we just keep factoring? And the problem is sometimes you can't keep factoring a quadratic because its only factors are imaginary or like nasty quadratic formula. So we could have quadratics left over if they're irreducible, if they can't be factored down anymore. Now, depending on what you get in step 2, you're going to be pointed 2 different directions for step 3. So we'll just say 3 and 4, they kind of go together. It depends on what you get in step 2. If you get linear factors, you're going to have to go ahead and make partial fractions for each of them. You're going to have to make partial fractions for each of them. And partial fractions for linear factors will look in this form. If you had quadratic factors, then you're going to go ahead and write partial fractions in this form. The problem is we're not going to know A's, and we're not going to know B's, and we're not going to know C's. So that's what the rest of basically the section is all about. How do you find the A's and B's and C's? How do you find the missing pieces? This table looks super intimidating, but don't worry, it's not. It's not as intimidating as it seems. So step 3, if you have linear factors, make partials from them. Step 4, if you have quadratic factors, make partials for them. Let me write in my own little step 5 and step 6. Step 5, multiply both sides by the common denominator. Poor kid, that's rough. Multiply both sides by the common denominators. Multiply both sides by the common denominators. It's going to make all of life so much easier. And then step number 6 is solve. Where do I put this? Let's do solve for. Solve for the missing variables. And there are 3 different techniques. Technically, there are 2 different techniques, like 2 approaches. A is going to be, which one should I do first? A is going to be group like terms. A is going to be group like terms. That's one way to go. B is a different approach, and the different approach is use strategic values. Strategic, specifically X values. I'll try to show you, hopefully we can get through one example of each approach. Hopefully. Group-like terms, use strategic X values, and no matter which one you use, somewhere along the line you're going to have some sort of system that you're going to have to solve. And it's going to be up to you. You can use some substitution, you can use some elimination. Somehow you're going to have like a system of equations that you have to solve. And hence why it's after section 7.1, 2, and 3. Because you've been practicing all that sort of stuff. Alright, partial fractions, little baby puzzles, we gotta break them apart. Let's see if we can get 2 examples done, okay? Here we go, first example. That's my shortcut, but you know what, we already just narrowed down. Ignore him. Please, here we go. This is an easy example. But it's not gonna be easy yet necessarily. Wait a minute, isn't this the one at the beginning of notes? So what are we doing? Cheating and going back and seeing what it was? No.
Oh.
We're learning how to get to the partial fractions. We learned how to go backwards and show that they match. But how can you actually figure out those partial fractions yourself? Well, step number 1, we ask ourselves the question, is it improper?
No.
What does it take to be improper?
Top
Degree has to be greater than the bottom. Doesn't the top lose? Okay, so it's not improper. Forget that. Okay, step number 2. Factor. Okay. Factor who?
The denominator.
Alright, let's factor. He's an easy one. That's part of what makes this easy. Because when we factor, hopefully you guys can see, I have an x and a 3 and an x and a 2, and who's going to be the negative? Yep, 3 is going to be negative, 2 is going to be positive. Step 2, done. Step 3, form partial fractions based on, actually steps 3 and 4. Form partial fractions. I'm not exactly sure where to put this so you guys don't think it's part of the process. I'll draw a little line to it, how about that? Partial fractions, we're going to go ahead and there we go. So step number 2, there he is. Step numbers 3 and 4, here they come. We need one partial fraction, it's linear, so we're just going to put one variable up top. We're going to form another partial fraction for the other factor, which is x plus 2. Now guys, in our table-y thing in the book, it says name that A1 and name this A2, but a lot of you, as well as I, don't really like those subscripts if we can avoid it. So can we just name him A and name him B? Is that alright? whatever, it's one variable, it's not a variable, no big deal. So step number 2, factor, got it. Step number 3, form partial fractions, got it. Technically 3 and 4, we don't have any quadratic-y ones to worry about, so no big deal. What's step number 5 say? Multiply both sides by? Okay. Who is the common denominator? Yeah, the whole thing. So we're going to multiply that side by the denominator, or what we do to one side, we have to do to the other. Let's see how much nicer this makes things. On the left, what happens when we multiply? Yeah. Our goal with this multiplication, step number 5, is multiply both sides. Our goal with this multiplication is to hopefully get rid of stuff like, hey, that whole denominator is gone. Sweet. We're left with just x plus 7 on the left side. On the right side, okay, this whole shebang needs to go to everybody. So, times a over x minus 3. Hopefully you won't have to write this every time, but just to make sure you guys understand the process. I'm writing it the long way the first time. Both terms need the entire product, x minus 3 times x plus 2. Both of them need it. But what do you guys notice about each of the terms? Yeah, whoever a was over, that's going to go ahead and cancel because they're going to match. Whoever b is over, that's what's going to cancel because they're going to match. And what do we have left? X plus 7 equals a times x plus 2 plus b times x minus 3. Now, at this point, it gets weird until we get used to it, because we look at this and we're like, oh my goodness, we don't have x, we don't have a, we don't have b, this is awful. Except, we don't care about x. We care about who we're missing. We know where the x's are supposed to go. We're totally fine with all of our x's. What we need to know is a and b. What we need to know is a and b. Step number 6, what does it say? What's our first strategy we could use? Group like terms. Let me show you that one, okay? Group like terms. Let me see if actually, let me try to show you my 2 strategies right here. I'm going to go ahead and divide it. Okay, so we're going to do the like term strategy and show you how that one works. And then we're going to do the strategic values strategy. And guys, both of them work. Both of them have their pros and cons. One's not necessarily better than the other. It just depends. So I'm going to solve this 2 very different ways. So here's what we're trying to solve right here. And there are 2 different ways of doing it. Okay? So, like terms. Let me go ahead and zoom in on that. If we were to do like terms, here's what we would do. We would go ahead and say, all right, over here we have 1x plus 7. And over here we have ax plus 2a, I'm distributing, plus bx minus 3b. And we're going to say, you know what? I see some like terms in here. I see x terms. Careful of the signs. And I see constant terms. The x terms have x's, the constant terms don't. The x terms have x's and the constant terms don't. From this, we can go ahead and see, or make the following equations. Now, this first time I'm going to go ahead and show it super explicitly, like with all the work shown up. We could say that 1x had to come from ax plus bx, and 7 had to come from 2a minus 3b. Now pause and think. Does that make sense? Ax plus bx had to combine to make 1x, and 2a minus 3b had to combine to make 7. It's weird, but it's right. Now, if only we could get rid of those x's. Wait a minute. What does everybody have over there?
No.
Oh. So can't I just say, instead of writing the whole terms, can't I just put the coefficients and say 1 with the x terms must have come from A plus B with the x terms? Or another way of saying it, divide everybody by x and now he's gone. You could divide everybody by x and now he's gone. What do we have? A baby system of equations that we need to solve. How do you want to solve them? I don't know. What do you guys want to do? Substitution or elimination? Substitution? Alright, fine. So let's go ahead and solve for, I don't know, A. A equals 1 minus B. Let's go ahead and plug and chug. We get 7 equals 2 times 1 minus B minus 3B. We're just solving with systems, right guys? We're solving our system. 7 equals 2 minus 2B minus 3B. From that, we should be able to, fairly quickly subtract the 2, that's a 5, negative 5. Say they got B equals negative 1. Yeah, I'm just trying to save on room because I'm running out. So B equals negative 1. And once we find B, where do we take him? Who's waiting just to be plugged into? Yeah. So let's go plug him in. And A would end up equaling 1 minus negative 1. 1 plus 1? 2. We found A, we found B. Go team. So what's the other method? The other method says, this one's a little bit crazy, for strategic values. I'm going to just tell you what the strategic values are for this problem. The strategic values for this problem, sometimes there are very clear ones, sometimes there aren't. The strategic values are negative 2 and 3. The name of the game is plug it in, plug it in. What? Really? Yeah. Plug it in. Negative 2 plus 7. Where am I plugging it into? My equation, of course. Equals A times negative 2 plus 2 plus B times negative 2 minus 3. Now hold on. Negative 2 plus 2. Isn't that just 0? Now what's negative 2 minus 3? Negative 5. Why was negative 2 so nice to plug in? What happens over here?
0. That's where the value.
Oh. So hold on. 5 equals negative 5B? Yep. So B equals negative 1? Oh, that's kind of spiffy. If I plug in a 0 of my factor up above for my strategic value, things simplify quite nicely. Now I have B, that's all well and good. I could technically do it again for x equals positive 3. Some of you are like, you can plug it in. I know. But we could also just do 3 plus 7 equals A times 3 plus 2 is 5, plus B times 3 minus 3 is 0. What was nice about that?
The B cancels.
B's gone. 10 equals 5A, A equals 2. Okay, now once again, 2 separate ways to solve one common problem, right? So where does this all get us? We put this all together to say the following. The original function, x plus 7 over x squared minus x minus 6 is equal to, take the A, take the B, put it in the proper spot. 2 over x minus 3 is a partial, plus negative 1 over x plus 2. And if you guys go to the beginning of our notes, does this match what we found to be, or what we saw to be a partial fraction? You guys are too excited about leaving. Alright, kiddos, start your homework. You can do the easy ones and actually the hard ones if you're creative. Happy 2-day weekend.
If you're doing the
And you have the rest of your Friday.
thing and you get like